and combining like terms and things like that for monomials. So now we're going to expand a little bit. It won't get too difficult. It's just a matter of understanding what the appropriate approach ought to be. All right. So let's take a look at number one here, and this takes us back a couple of, like, I'd say about a week anyway, a couple of days. If you have a number in front of a set of parentheses, that number should be distributed to each term within the parentheses. If there isn't a number in front of the parentheses, there's an assumed 1 there. All right, so in front of this set of parentheses over here, I'm going to pop in a 1 because there's a negative sign there already. That makes that 1 a negative 1. All right, so I'm going to distribute through the 2 to each term in that first polynomial. All right. Then I'm going to distribute through the negative 1, sign goes with it, to each term in the second polynomial. All right, also known as a binomial. First one's a trinomial, 3-termed expression. The second one is a binomial, 2-termed expression. All right, this should all be familiar. At least, I think you learned this the first time, number of terms and things like that back in like 6th grade. All right, so it's just a refresher, constant refresher. All right, so 2 times x squared. Well, you can't just multiply 2 by the number x squared. There's an assumed coefficient in front of the x. The 2 gets multiplied by that 1, that assumed coefficient. So we're looking at 2 times 1, or 2x squared, 2 times negative 5, so negative 10x, and then 2 times the constant, 2 times 3 is 6. All right. For the second binomial, we don't have to worry about slipping in any more coefficients. They're already there. Negative 1 times the 3 gives you a negative 3x squared. Negative 1 times 7 will give you a negative 7. Then from here, it's a matter of combining like terms. Right? So remember, like terms are terms that have the same variables with the same powers. All right? So the 2x squared can be combined with the negative 3x squared to give us a negative 1x squared. But you could just write negative x squared. All right. The negative 10x doesn't have a counterpart, so that just comes along for the ride. All right. We work in order of powers, so highest power to lowest power. That's, again, called descending order. All right, so we always want to have our answer in descending order. Now, the 6 plus the negative 7, that'll combine to give us a negative 1. And so the final simplified answer here would be negative x squared minus 10x minus 1. All right. Again, we don't really need much with the technology here, but I did want to show you very quickly that there's a way using graphing calculators and Desmos. I'll do it with both just to verify your answer. I'll do it with the graphing calculator first, assuming it wants to work, because people were saying yesterday that it's been troublesome. People as in other teachers, sorry. Students, I don't know. If you have the calculator emulator, then wonderful, but I wouldn't expect that to be the case. So what you would do in a graphing calculator, I got all this from another class, type in the original expression. Well, the short answer here is, bless you, you type in the original expression, type in your simplified expression, and see if they give you the same graph. All right, so that's what I'm doing here. So original expression, simplified expression. Now we want to see if they give us the same graph. The thing is, when you're dealing with two expressions that are somewhat complicated in appearance, sometimes if you just hit graph, you won't see the picture. You know, just like in Desmos, sometimes the zoom or the window isn't set up the way you want it to be. So the recommendation here is to go to the table. So second graph, see how it says table above graph? Second graph will bring you to a table of values. If the values in the two columns match up, the y1 and y2 columns, what that means is that for y1 and y2, given a particular x value, we're getting the same result. If that's the case, then y1 and y2 must be equivalent to one another. All right. Oh, yeah, I just hit graph accidentally, but you see my point. Nothing shows up, so it's not really very helpful. All right. But the table gives you a good look. If you see y1 and y2 matching each other, then you know that your two expressions are equivalent. Now, the issue could be, or one issue that you might come up against would be if you didn't simplify enough. Like maybe there was more you could do, but you did everything to that point correctly, it would still verify in the calculator. Like, for example, if I typed in the 2x squared minus 10x plus 6 minus 3x squared minus 7 instead of my simplified answer, so I forgot to combine like terms, the calculator's still going to say that everything is fine. All right? So you just got to be careful. So you just go through all of your algebra before you start the process of checking. Now, the same idea would be true on Desmos. So if I typed in my original expression minus 5x plus 3, close it up, minus parentheses 3x squared plus 7. Keep looking at the wrong thing, so I just want to make sure I'm typing in the right stuff. You get this nice looking parabola. That's fine. With Desmos, as you know, you don't really have a choice in whether you want to graph it or not. It always graphs it. So you're going to get the picture. It's just a question of whether that picture is going to show up in the window that you have. So here's my simplified. And you'll see the two graphs are identical. Well, one's blue. But they're the same picture. Right? So we're in pretty good shape there. Now, if you wanted to go with the table of values approach like we did on the TI, you could do that. Just hit that little gear icon and tap on table for each one. The table should be the same. 15, 8, negative 1, blah, 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 15, 8, negative 1, blah, blah, and blah. Right? So it's a good way to check your work, but you have to carry out the algebra anyway. So a lot of people just kind of skip the technology part. Just because it's like, well, if I got to do the algebra, then, you know, like, why go to the technology? But again, to check your work and even for a multiple choice question to know that you can get the answer without doing the work, that's pretty solid. All right. For number 2, this is more in line with what we were doing over the last couple of days. So we have order of operations. We have entire expressions raised to powers. So we have to address that first. So the first thing I would do is take care of that negative 4. That negative 4 can be thought of as negative 4 to the first power. Everything, if you're going power to a power, everything that's in the parentheses needs to be thought of as an expression raised to a power, all right? Even if it's just a simple number, all right? So negative 2 would also be considered a power of 1, all right? So we run across from left to right, and this is, it's pretty common that people are skipping this step, all right? I'd say probably not so much in this group, but throughout the day yesterday, I noticed that people just wanted to take that negative 4 and multiply it by 3. Take that negative 2 and multiply it by 4. Folks, the computers go away. We don't need the computers. So what we're doing is we're multiplying all the exponents, all right, by whatever that outer exponent is. And that's important to remember because if you have that in mind, I'm multiplying all the exponents inside by the exponents outside, then when you see an expression or a term that does not have an exponent, then you would ask yourself why. Wait, where's the exponent for this one? Oh, that's the one where I put a 1. All right, and then things get a little easier. All right, so negative 4 to the 3rd, x to the 9th, y to the 12th, negative 2 to the 4th. Now that x also needs an exponent, so I'll pop that in there. X to the 1st, so x to the 1st becomes x to the 4th if I multiply those exponents. So x to the 4th, y to the 20th. Now I want to take care of the numerical values. All right, so negative 4 to the 3rd, well, that would be negative 4 times negative 4 times negative 4. That's 3 negative symbols. Negative times negative would be negative, because negative times negative is positive. Multiply positive by a negative, that would be that third negative. The result is going to be negative. So I can address that part first. Then I would think, okay, well, what's 4 times 4? 16. Times another 4, 64. When I multiply by 4, at least for larger numbers, or 8 or 16, whatever, I think of it as powers of 2. Right? This is what they were trying to teach you. Or, I mean, they taught you. It's just a question of whether it's stuck way back when in elementary and middle school. When you multiply by a number, you should be thinking about how that number is bonded to another number using multiplication. All right, number bonds, you might remember that. So when I multiply by 4, I don't actually multiply by 4. I double and then double again, because 4 is 2 times 2. It's 2 to the second power. So if I had to take 128 and multiply it by 4, I'd say, okay, well, what's 128 times 2? All right, so that gives me 256. Then I would double that. That's the same as multiplying by 4. That would get me to 512. All right, the idea is that it was supposed to sort of train you towards mental math. All right, whether it worked or didn't is a different story, but at least give it a shot. Try to do it in your head and then go to a calculator. So negative 64, x to the 9th, y to the 12th. So with a negative 2 to the 4th power, that's negative 2 times negative 2 times negative 2 times negative 2. That's 4 negatives. So our answer is going to be positive. All right, so now I just want to think about what 2 to the 4th is. Well, 2 times 2 is 4. All right, so that's 2 to the power of 2. Multiply by another 2, that's 2 to the power of 3, which gives me an 8. Multiply by another 2, so double, 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 I get a result of 16. All right. So now I have to take the negative 64 and multiply it by 16. Again, go to a calculator if you want, but negative times positive I know is going to be negative. 16, we just figured out, is 2 to the 4th power. 2 to the 4th power is 16. That means that if I take that 64 and double it 4 times, I'll get my answer. All right, so 64, all right, I want to double it, all right, so that's going to be 128, then 256, then 512, then 1024, all right. Again, not a requirement that you do it in your head. But if you've ever been fascinated by somebody's ability to do mental math, you got to understand. It's like an athlete. I'm just trying to think of it like a reasonable sport, like somebody who's a good pitcher. You only see the outcome. You go to the baseball game and you see a kid throwing 100 miles an hour. You're like, wow, that kid's so good at baseball. You don't see the hours upon hours behind the scene that they're putting in to get that good. All right, the folks who have good, strong mental math ability, it didn't just happen overnight. All right, it happened through practice. All right. So, x to the 9th, x to the 4th. Keep the base out of the exponents, x to the 13th. All right. Y to the 12th, y to the 20th. Keep the base out of the exponents, y to the 32nd. All right. So now what we're going to learn is how to multiply polynomials against other polynomials. All right. We'll start off with a monomial by a polynomial, but we're going to kind of bridge out from there. I'm going to show you using a geometric approach, as in geometry, as in like shapes, just to kind of get you the idea. First off, I wanted to kind of remind you that I don't think is something that necessarily needs too much instruction, but area of a rectangle. I don't need a thicker marker here. Most people don't have trouble with that one. It's all the other ones Like, oh, what was the area of the circle formula again? You know, things like that. Area of a trapezoid. So, area of a rectangle, and we know what a rectangle looks like. Rectangle has the two dimensions that we care about, length and width. They're interchangeable because multiplication is commutative. So I'll call this one the length, and I'll call this one the width. We know the area of a rectangle would be length times width, or width times length. It doesn't, again, it's commutative. It doesn't matter what order you do it in. All right? So you look at that and you say, okay, well, that has nothing to do with what we're learning. Well, it does, because anytime you multiply two factors, you're in fact finding an area. All right? Especially when you're dealing with symbolic notation, as in variables. All right? Again, folks, we don't need the phones, we don't need the laptops, we don't need it's all pencil paper. I gave you packets. Folks wanted packets, I gave you packets, but technology doesn't need to happen. All right? So if we're multiplying two factors, we're really finding the area, assuming that those two factors are dimensions. All right, so this isn't really a case where the 3n is the width or the length, and the n squared plus 2n is the width or the length. It's that we have two dimensions of a potential geometric figure. All right, so what I would do is look at this and say, all right, well, one of these factors, and by the way, I keep saying factors. Factors are numbers that are part of a product. Product is multiplication. All right, so when I multiply two things, each of those two things is a factor. All right, so I'm going to call one of these sides 3n and the other side n squared plus 2n. All right, that seems reasonable enough. If I said draw a rectangle and label it using the two factors, is probably what you come up with. But what makes this unique is the sum. All right? This sum here, this plus, is telling me that I can have part of the length of this rectangle be represented by the n squared and the other part be represented by the 2n, because if I add them together, that would give me the whole length. All right, so it's this entire distance that's represented by n squared plus 2n. All right, so what I'm going to do, oh, I hit zoom, wrong thing, is I'm going to break that up. All right, I'm going to split that length. I actually didn't need this. So that one part of it, and it doesn't have to be down the middle, so I'll just kind of skew it a little bit. I'll put it like right here. One part of it is the n squared, and the other part of it is the 2n. The idea being that if I told you that an entire length is, let's say it's equal to 10, then couldn't part of it be 7 and the other part be 3? 7 plus 3 is 10. That would give you the whole length. I'm going to drive 10 miles. All right? So I drive 7 miles, stop at a rest stop or something, and then go the other 3 miles. I still traveled the 10 miles. I just did it in pieces. All right? That's the idea. All right? So what we're actually doing here is we're finding the area of each part. I'm taking the 3n, multiplying it by n squared. I'm taking the 3n and multiplying it by 2n. All right? So we've taken a situation where we're multiplying polynomials, or monomial by polynomial, and breaking it down so that it's really just separate cases of multiplying monomials. So the 3n to the first multiplied by the n squared, and then 3n to the first multiplied by 2n. All right, there's an understood coefficient of 1 here. So I would be looking at one area that's equal to 3 times 1 is 3, n to the third. 3 times 2 is 6, n to the second. If I want the area of this figure, all I'd have to do is add those two pieces together. All right? So the result, the area, would be 3n cubed plus 6n squared, because they're both positive. and we're adding it together, because if I tell you that I have a piece of property that has an area of 100 square yards, and I buy an extra piece of property to go right next to it with also an area of 100 square yards, don't I really have 200 square yards? I just put it all together. All right. Now, what you'll see as a shortcut for this is the idea that, all right, well, I took the 3n, I multiplied it by the n squared. So I took this 3n and I multiplied it by n squared. I also took that 3n and multiplied it by the 2n. All right. So I also took that 3n and multiplied it by the 2n, in each case multiplication. All right. And if you just carry down that sign, then you'll have your simplified form. But in the past, I'd have many instances where students would say, okay, we did that process you told us about, it was fine, but we don't know why we're doing that. Right? What was the justification for that? Right? And so this is the justification. I mean, technically, anytime you multiply a number by another number, you could draw a picture, a rectangle, multiply those two numbers and say, well, it's the area. Right? So for the next one, I'll draw the picture, and just understand, I am going to ask you to justify using geometry on a test. All right, so this technique, you don't like it. There's easier ways to do it. It's fine. I'm speaking in generalities. I'm sure there's somebody that doesn't hate this. But it's the theory behind it. It's why things work the way they do. Right? Skills are one thing, but understanding the why, that's important. All right. So for number 2, so I'm basically going to carry out this process again. Got a nice little rectangle here. One dimension is negative 7c. And you'd say, oh, you can't have a negative side for a rectangle. Your analogy is falling apart. Well, we don't know what c is. If c is negative, then that whole side would be positive and it would be perfectly fine. All right. Now, the whole length of this side here would be 5 minus 2c squared plus c cubed. But what we're saying here is that you can break up that area. All right, we could break up that area, so instead of saying all in one shot, we have the 5 minus 2c squared plus c cubed. We have 3 separate regions because it is a trinomial. One of them would have a length of 5. The other would have a length of negative 2c squared. And the other one would have a length of c cubed. All you're doing when you're distributing the polynomial is you're finding the area in each one of these regions. I purposely drew them so that they would be a little bit different in size, just because we don't assume it's always going to be 1/3, you know, so just try to exaggerate the difference a little bit. But negative 7c times 5 would be negative 35c. Negative 7c times negative 2c squared would be 14c cubed. Negative 7c times c cubed would be negative 7c to the 4th. All right? So each one of these areas gets added together, but we'll do it in descending order. All right? Highest power first. So the negative 7c to the 4th comes first. Then we have a positive 14c cubed. And then we have a negative 35c. So that would be our simplified form, right? And again, we would have gotten the same thing if we distributed the negative 7c to each term through multiplication. But you kind of lose a little something if you just jump right to that process. All right. All the remaining examples, even the ones with fractions on this page, they all kind of follow the same, well, they definitely follow the same strategy. So I'm going to hop over now to double distributing. Polynomial by polynomial. Interesting stuff. It's no more difficult than what we just did, using this geometric technique. I just try to make my work look consistent here. That coffee was too hot. Coffee's too hot. Burned my mouth. I'm going to be paying a price for that for the next 2 weeks. I thought that was the one I cooled off. Actually, I don't think I cooled off any of them. What I usually do is I dump a little cold water into the coffee when it comes right out of the Keurig, and I forgot to do it for this one.
Mr. Cam, that hurts to see.
Oh, the
Water.
yeah, it's water. It's the roasted mouth that I'm running into a problem with here. Whew. It's like when you like, I don't know if you've ever had a Hot Pocket. You take one of those right out of the microwave and you're starving, so you're like, you just bite right into it, and then you have the swollen roof of your mouth for the next month and a half. Yeah. For me, it's not that bad right now, but it's not good. It's quite painful. So anyway, binomial and a polynomial, binomial, other binomials, trinomial, any nomial, all right? So if we look to number 12, we see we're taking x plus 4 and multiplying it by x plus 5. So what we're doing is, I'm going to make a nice little rectangle here, kind of exaggerate it a little bit. We're taking 2 dimensions of a rectangle, one of them x plus 4. I'm just going to write it like that. And the other x plus 5, just for space. Now, if I say, okay, now multiply them and find the area, that would be great, except the reason why we're jotting it down like this is because we don't know how to find the area quite yet, or x plus 4 times x plus 5. So what I'm going to do is pretty much what I did on the previous page. That is, break up each dimension based off of the 2 values that I see. I have an x plus 4. That means one part of this is x, and the other part of it is positive 4. All right, so I'll just kind of split it like that. I don't know which is bigger, so I'll just kind of make it a little lopsided. All right. Same idea for the base dimension. One part of it is x, and the other part of it is 5. So I'll do it like this. I'll throw the x over here. I mean, the accuracy of the diagram isn't really that critically important. It's just they're both the same x. So I kind of want this distance here to be roughly equivalent to this distance here. You know, just for personal satisfaction. But one part of this is x and the other part is 5. I think, hopefully, if you really think about it, we'll all agree that if I take this and add it to this, x plus 4 would be the result. All right? As in, not the numbers, but the dimensions. If I take this dimension and add to it this dimension, the result would be whatever you would get if you took x and added 4 to it. All right? So then when you do it like this, it's like, okay, so I'm finding the area of each piece. Well, that's easy enough, because to find the area of this piece, all I'm doing is taking this dimension and multiplying it by this dimension. And I have had the question in the past, how do we know this dimension? Well, it's a geometric rule. All opposite sides in a rectangle are congruent. All right? Opposite sides in a rectangle are equal in measure to one another. So if this side here is x, so is this one, and so is this one. If this side here is 5, then so is this one and this one. If this side is x, then so is this one and this one. If this side is 4, then so is this one and this one. So instead of labeling up this entire diagram, which could take time, which does take time, we just think about it and say, okay, well, what would the dimension, that missing dimension, be based off the information I have? But now that it's labeled, it's like, all right, well, let's do it. You know, we have x times x, x squared. 4 times x, 4x. We'll do it this way. 5 times x, 5x. And then 5 times 4 results in 20. All right, so now we have all of the areas for this mega rectangle. All right, so what do? Well, we want to know the total area. We want to know the combined area. So combine them, add them all together. So we'd have x squared. I got a 5x, I got a 4x, and I got a 20. I have some like terms here that I could put together. That would give me a 9x. But everything else is a singleton. It doesn't have like terms. So the x squared comes along for the ride, the 20 comes along for the ride. And so we end up with x squared plus 9x plus 20. I was like, oh, that's great. That took forever. Which is why, you know, I'm not going to ask you to do this like 10 times on a test, but you know those free response questions, the ones where you show all work. This will be the all work that I want to see, justified by showing the areas. All right. Now, there is another way to do it, but basically it amounts. Thank you. It basically just amounts to taking each term of your first polynomial and multiplying it by each term of the second polynomial. All right, so I'm going to take this x and multiply it by x and 5. That'll give me, let me actually get a different highlighter color here. Let's see here. I'm going to go with classic yellow. The x, I'm going to multiply it by the x and the 5. That would give me the x squared and the 5x. Then I would take the 4, the positive 4, really, the sign always comes along for the ride. The positive 4, multiply it by x and 5. That would give me 4x and 20. All right, so each part of the first binomial gets multiplied by each part of the second binomial. All right, so the way that would work is to say, all right, well, I'm going to take, in number 13, I'm going to take the x, multiply it by an x and a 7. All right, you got to get to a point where you're pretty proficient with multiplying monomials in order to be able to handle this, because you don't want to have to write out every time, all right, this has got a coefficient of power of 1, coefficient of power of 1. All right, we got all our variables taken care of. You know, like, it's good to get started and understand the concept, but eventually you want to get past that. All right, so 1x squared times 1x squared would be 1x to the second, keep the base out of the exponents. The 1x squared times the 7, well, 7 times 1 is 7. So plus 7x to the first. We'll get rid of those powers of 1 after the fact. The negative 2 multiplied by each one of these terms. Negative 2 times 1 is negative 2. So negative 2x to the first. Negative 2 times 7 is 14, or negative 14, because negative times positive is negative. All right, we have our like terms here. So 7 minus 2 is 5, so 5x to the first. So I'm just going to write it as 5x now. Bring down the 14, the negative 14, and bring down the 1x squared, which is just x squared. Now, it looks like I'm missing something. I said 7x to the first minus 2x to the first. It's like, well, what's the relationship between these two? You got to think about that. Well, the 7x minus 2x is a positive 5x. All right, the sign always comes along for the ride as well. All right, whether it's through combining like terms or multiplying monomials, whatever it is, the sign always comes along for the ride. All right, so Yeah, you do all this without the picture, but we want the picture. Now, when I ask you to do homework, I'm not going to ask you to draw. I mean, the picture it takes a little time. I'm not going to ask you to do it for every problem, but I will recommend that you try it for a couple of problems. Right? Get a handle on the picture approach, drawing out the areas, because that's an important part of understanding what this stuff is all about. And I can tell you, I mean, it's hard to look 4 years into the future and see that as something that matters at this point. But I can tell you that as you progress through the next 4 years, 3.5 now, roughly, you're going to find more and more of a need to understanding the underlying concept and not just following the steps. All right, because following the steps will get you stuff right now, but when you have to apply this later on, you're gonna wonder why you can't figure out stuff that everybody else is already able to figure out. All right, and having nothing to do with ability, having everything to do with the knowledge that you should have but you don't have. All right, so yeah. Anyway, what we'll do for homework is just the problems that we skipped along the way. So pages 16 and 17. All right. So mixing and matching, whatever makes sense for that.